Hi, this is the last unit on SGD, and this unit is going to be about one theorem that provides insight into the behavior of SGD as we reduce the learning rate, the temperature. So you've all seen this slide before, and this is the phenomenon that this theorem is going to address. So this is the loss over time as we reduce the learning rate. So at the first learning rate, the loss reaches an equilibrium. Then we drop the learning rate by a factor of 2. The loss drops, reaches an equilibrium. We reduce the learning rate by a factor of 2, it drops again. So what we want to understand is, in a more precise mathematical way, what is the relationship between the learning rate and the loss value? And so the idea is that there is some function of the learning rate, which is the converged loss value at that learning rate. So there's this function loss. There's this function that is the loss as a function of the learning rate. And if we take the limit as the learning rate goes to 0, we can think of that as the loss at learning rate 0. And that is presumably the loss of some locally optimum value of the parameters, some phi star. Okay, so now the question is, how well behaved is this function, loss as a function of learning rate? And if it's really well behaved, if it's differentiable, then we should be able to do a Taylor expansion for this function, right? So if we do a Taylor expansion, then loss as a function of the learning rate is equal to this limiting loss, the loss at the local optimum, plus the first order Taylor term plus higher order terms. But I'm just going to focus on this first order Taylor term. What's this first order dependence on the learning rate? So this first order dependence on the learning rate is the derivative of the loss as a function of the learning rate at learning rate equals 0. Right? That's the way Taylor expansions work, right? This is the derivative at 0 times the deviation from 0. Okay, this thing, if we interpret loss as energy and we interpret the learning rate as temperature, this is a heat capacity. It's the derivative of the energy with respect to temperature. So this is going to be a heat capacity theorem. I want to make one more point before we move on. Let's suppose we're in the region where this linear relationship holds, where we can ignore the higher order terms. That means every time we drop the learning rate by a factor of 2, we get halfway to the optimum, right? If this goes down by a factor of 2, we're halfway to the optimum. So that says that, that this drop should be half as big as that drop. And if we did it again, we would get a drop half as big again. Each time we're getting halfway to the optimum. So then we get this geometric series. And that pretty much agrees with practice. And at iClear 4 years ago, I was talking to Leon Botu, and he made this claim that you get that there's this geometric series. And he said there was some theoretical motivation for that, but I couldn't remember that. And when I was teaching this course a couple years later, I tried to reconstruct it, and that resulted in this theorem. And I talked to Leon Botu, and he did not seem to know this theorem. So this theorem is original with this class. Okay, so let's state the theorem. So let B, I'm going to use little b. We've been using little b to index batch elements. I'm just going to use it to index some random training point. So the loss at little b is the loss at that training point at the parameter setting phi. And I'm going to let GB denote this gradient at the optimum. So GB is the gradient at the optimum. And then the theorem says that this term, this heat capacity at 0 temperature, is exactly equal to, and I'm pushing some mild assumptions under the rug at the moment, but under these mild assumptions, this is exactly equal to 1/4 the expectation over the training points of the norm squared of that gradient. So you know you've got a good theorem when the statement is, really clean, just a few symbols. Okay, so I'm going to drag you through the proof. This might be a little painful, but at least you'll get a sense of, it's not going to be that painful, I think. So we're letting little b index in particular training points. And so I'm going to be interested in little b at a parameter vector, which is the optimum plus some delta. And I'm going to take a second order Taylor expansion for this loss at b around this point, thinking of this delta as the deviation in the Taylor expansion. So here's the Taylor expansion. So the total loss is the average over training points of the loss at that training point. And here's the Taylor expansion. So the loss at a small deviation from the optimum is the loss at the optimum plus the gradient of the loss times the change. And although the total loss is 0, the gradient on a particular point is not 0. So this is a meaningful term in this Taylor expansion. And then we're going to take a second order approximation. So we're going to take 1/2, and this is the second derivative. The Hessian matrix at b is the second derivative of this loss function. This loss function is a function of a vector, so its second derivative is a Hessian matrix. And I'm going to assume that the optimum occurs at a bowl, at a locally quadratic bowl in the loss function. And what we get is that the average of the gradient at that optimum point has to be 0 because it has to be optimum. And the average Hessian, which is the Hessian of the total loss function, I'm going to assume is positive definite. So it's a well-defined local optimum. Now, at a given temperature, we have a stationary distribution. So I'm going to let Qn denote the stationary distribution on the vectors at that temperature, at the temperature eta, learning rate eta. But I'm going to do a change of variables. I'm going to center my vectors at the optimum. So I'm really interested in the distribution over delta phi, where delta phi is defined to be phi minus the optimum. It's the vector from the optimum. So I'm going to move the origin of my coordinate system to phi star. And then I'm going to write the loss at a temperature or learning rate eta to be an average over drawing the delta phi from the stationary distribution we've reached, and the average over drawing a random training point of the loss of that training point at the optimum. That's going to be this value, plus the gradient, and for a given b, this gradient exists, is not necessarily 0, times the change, the delta phi, plus a second order dependence on delta phi, which is determined by the second derivative of the loss function at that b. Okay, now what I'm going to do is I'm going to push these expectations into these three terms. So if I push the expectation into the first term does not depend on delta phi. That's just the loss at phi star. So this term becomes the expectation over b of the loss at b of phi star. So that's just the loss at eta equals 0. And then I'm going to get an expectation over delta phi. These two terms depend on delta phi. This is the first term. I'm going to push the expectation over b into these terms. So when I do that, I push the expectation over b in here, I get the average gradient times delta phi. Now the average gradient is 0. So this term goes away, right? In the next line, that term's gone. And then I'm pushing this gradient, this expectation over b into this term, and it goes in all the way inside to the h, and I get 1/2 the vectors inner product through the average Hessian. Okay, so I get the loss. So I get the loss at eta is the loss at phi star plus this middle term went away, plus this second order dependence. It's looking at the average Hessian. Okay, now how am I going to prove this theorem? I sort of dragged you through that. But let me give you the high level idea. and if you remember the high level idea, you can sort of, at least that's a piece of this proof that you'll be able to remember, I hope. There's a stationary distribution. This stationary distribution has some width. If we had a distribution that was too wide and I did an update and I took a step of gradient descent or a couple steps of gradient descent, the steps of gradient descent would contract it. If it was too narrow, the steps of gradient descent would expand it. And it's sitting there at a stationary distribution because the steps of gradient descent don't move it, right? The average motion over this stationary distribution cancels out and it's stationary. So what I'm going to do is I'm going to say the distribution has to be the same before and after I take a step of gradient descent. And I'm just going to write that equation. So I'm going to look at how wide it is. And by how wide it is, I mean the expectation over drawing this delta phi of the norm of that phi. What's the expected norm of the weight vector under this stationary distribution? And that's a measure of how wide it is. Okay, so what I'm going to say is it has to be just as wide under the station. When I take one step of gradient descent, the width has to be the same. So what I've written here is an equation that says the width after a step of gradient descent. So this is a step of gradient descent. This is the first order Taylor expansion of the gradient at point B as a function of this. So this is just the update equation of gradient descent. We take the parameter minus eta times the gradient at B. And the gradient at B is going to be modeled as the gradient at the optimum parameter vector plus a deviation that depends on how far we are from the optimum parameter vector, which is written this way. Okay, so this is saying the average size of the vector after an update has to equal the average size of the vector before the update. Now what I'm going to do is I'm going to take the size of the average vector after the update, and I'm going to expand this into the norm of phi squared minus twice this inner product plus the norm of this vector squared. And the norm of phi squared cancels is this term, right? So that goes away. So I get, so when I subtract that from both sides, I'm going to get equals 0. And what I have left is twice the inner product plus the norm of this term, right? So I get this expression. Now I can take this expression and just rewrite it, right? I divide by eta, and this expression equals 0 gives me this equation. And the reason I've written this as this way, I've also divided by 4. The reason I've written it this way is because if you look at the previous slide, this term is expressing the change in the loss function. And now I've got a different, and what I've just got is a different expression for that term. So that term is equal to this. So I can plug this expression in here. I've got an expression for that, and I get this equation. Okay, so now I've got this equation, and this is the change in loss as a function of eta. So the change in loss as a function of eta divided by eta is the gradient, or the limit of that as eta goes to 0 is the derivative of this with respect to eta. So I take this deviation, divide by eta, and that is the derivative. So the derivative is the limit of this thing divided by eta, which is now 1/4 the limit as eta goes to 0 of this thing. And as eta goes to 0, the stationary distribution, if the Hessian is positive definite, the stationary distribution is contracting to the point phi star. So in the limit as eta goes to 0, this delta phi is going to 0. So in this limit, this term is going to 0, and the limit is equal to this expression, and we're done. So Apologies if that was too dry, but the theorem, let's go back to just the statement of the theorem at the top. This is something that should be empirically verifiable, although I don't know, I haven't pursued that. And the result is pretty. And if you just remember this trick of saying the width of the distribution has to be the same before and after an update, if it's a stationary distribution, and that insight drives the whole theorem. So you could probably just, if you don't remember the theorem, if you really had to, you just take that insight and you could derive the theorem. Okay, thank you. We'll stop there.